What's up, scholars? Today is a good day because today we get to talk about circles. Now, what is a circle? It is the set of all points that are all points in a plane that are equidistant from a single point. Now we have to call it in a plane because if it was the set of all points that were equidistant from a single point in 3D, that would be a sphere. But we are just talking about, you know what, I'm calling it good. A circle in 2D, the set of all points that are equidistant from that center point. We of course know that the distance from the center point to the outside, that's called our radius. Let's talk about a whole bunch of other lines that interact with our circle. So we've got our radius, which is the distance from the center point to the outside edge, any point on a circle. Any point on a circle. The radius would be the same if it was drawn over here or drawn up here. Those would all have the same distance. Now, let's get out some different colors, shall we? We could have a line segment that goes from a point on the circle to another point on the circle. If we drew a line there, this is what we call a chord, not to be confused with the musical chord, of course. This is the geometric chord. Now let's draw a special chord that goes through the center. This, as you also may already know, this special chord that goes through the center of the circle is called the diameter. And we know the diameter is twice the length of the radius. Diameter is twice the radius. So those are the two segments that can interact with the circle, a chord, and a diameter. What about some lines? Let's draw some lines through this bad boy. A line that goes all the way through the circle that intersects the circle in two places is called a secant. And last color, what should we use? Obviously blue. That's really purple. So we had a chord that was a segment, went through the circle, a diameter, a special chord that goes through the circle's center, a radius that goes from the circle's center to any point on the outside. A secant is a line that goes through the circle that intersects the circle in two places, and a super special line called a tangent that only intersects a circle in one place. Tangents are all kind of interesting. They intersect the circle in one place. Now, this is, of course, not to be confused with the tangent we talked about before, which was the ratio of the opposite side of a right triangle to the adjacent side of a right triangle. This, instead, is a tangent line, which means it's a line that intersects a circle at exactly one point. And that point is called the point of intersection. Let's draw a line here. Ooh. point of intersection. Speaking of intersection, what kinds of intersections do we have when we talk about two circles together? Well, slide that sucker up. We could have two circles cross each other like this, that intersect in two places. This kind of looks like a Venn diagram, right? You guys did some of that probably in algebra. Or we could have tangent circles, meaning they only touch each other at one point. I'm drawing all these circles the same size, but they don't really have to be. I mean, you could have a tiny little circle and a much larger circle, which seems to be the same size as the circle above it. So these would be tangent circles. Tangent circles. Or you could have circles that don't intersect at all. So we can have 2 points of intersection, 2 points of intersection. Tangent circles have 1 point of intersection, 1 point of intersection. Or, obviously, we could have circles that never touch each other, that are really good at social distancing. They could be away from each other. Or, now this is really cool. This is quite pleasant. They could share a center. So I could have one circle here. I could have another circle that shares that same center. And these, my friend, are called concentric. Concentric. Because together they have the same center. And these are examples of circles with 0 points of intersection. Cool. Let's get back to this tangent to the circle, though. Let's get back to the tangent to the circle. This is going to be, we got a dessert theorem coming up for you with this tangent of a circle. Dessert theory of the tangent lines. Before we can get to that dessert, it's time for a bean break. What's up, Bean? How you doing, kid? Enjoying the lesson? Oh yeah, it's a good time. I just chill and, like chew my bones and stuff. Okay, bye. See you later. Okay, we're going to have 3 theorems about tangent lines to circles. So, and the last one will be the dessert. It's going to be good. I hope you're not lactose intolerant. Anyway, go ahead, draw a circle. Draw a line tangent to that circle. And I say to you, let's call this line L. Let's call it circle O. We'll name it by its center. And I say to you that if line L is tangent to circle O, then line L is actually perpendicular to the radius. Let's call that point of intersection P, OP. So again, if line L is tangent to circle O, if line L is tangent to circle O, that's my symbol for circle. That is the center point O. If line L is tangent to circle O, then L is parallel to that radius OP. Boom. Why is this true? So real quick, I'm going to talk through an indirect proof. You don't have to know this. You don't have to write this down. This is just for interesting thought. An indirect proof of why this is true. So an indirect proof is where you assume something and follow that logically through to its conclusion, and you'll end up with a contradiction, which means the thing that you assumed at the beginning cannot be true, and thus you prove that the opposite of that is true. So, okay, anyway, indirect proof of this theorem that says if line L is tangent to circle O, then line L is perpendicular to the radius. So my indirect proof, I'm going to say that this is not the case. That OP is not tangent to, or is not perpendicular to L. So this is not a right angle. So I'm going to say that OP is not a right angle. So that means I could draw a right angle, right? I could draw some line here, and that would be the right angle, right? So now we have this right triangle that we created because we are assuming that OP is not perpendicular to L. It's not a right angle. So if it's not a right angle, I would be able to draw a right angle. I drew this right angle here and made this right triangle. And the nature of a right triangle is that the hypotenuse is supposed to be the longest side. But if we zoom in here, we see that X actually lies outside the circle, which would mean this side would be the longest side, which is a contradiction. That can't happen. So that means our original assumption that this was not a right angle here could not be true, so it therefore must be a right angle. So if line L is tangent to circle O, then line L is perpendicular to its radius. Now the converse is also going to be true. That's theorem 10.2. So theorem 10.2 says the converse, that if the radius is perpendicular to some line L, then that line L is tangent to the circle. If line L is perpendicular to the radius OP, then line L is tangent to circle O. Why did I pick a letter that looks exactly the same? I don't know, just did. Just what happened. So let's do an example where we use this sucker. Question is segment EF tangent to circle D? Well, we've got a triangle here. That must mean something. If EF was tangent to circle D, that would mean this was a right triangle. And if it's a right triangle, we know the Pythagorean theorem is true. So let's check that out. We are looking to see, is a squared plus b squared, does that equal c squared? Now which side is going to be c? It's always the longest side, so that's going to be where we plug in 25 squared. And how about 8 squared plus 24 squared? Well, 8 squared is 64, 24 squared. I don't know. I know 25 squared is 625, but I don't know my 24 squared. That is 576. Well, it's just for good measure. Yep. 625. Add up the left side. I don't know. 640 is not the same as 625. So the answer is no. It's not tangent because it's not a right angle. Alright, I promised you some dessert. It's time for the dessert theorem with tangents to a circle. Let's get us a brand new page. And here it is. The ice cream cone theorem. See, I told you were getting some dessert. Alright, draw please a scoop of ice cream. That's a perfect circle. Now we're going to draw a cone from that ice cream such that the sides of the cone are tangent to the circle. See, look! It's like an ice cream cone. Okay, let's give these some names. Let's call this circle P. It's named by its center. Let's call this, let's do X and Y and Z. Now, the ice cream cone theorem states that if two segments from the same exterior point, meaning point outside of the circle, two segments from the same exterior point are tangent to a circle, that those two segments are congruent. So if XY and ZY are tangent to circle P, then segment XY has the same measure as segment ZY. That is some beautiful, beautiful stuff. Now you might see examples where this extends as a line. Like you have a cone going up to infinity, but I'm more of a ice cream in a cup kind of person, so I don't want an infinity cone. Anyway, you might see it look like this, but the same will be true. And real quick, because I'm in the mood, I'm going to show you why that's true in a little thing I like to call a proof. I'm just going to talk through this proof. You don't have to write it down. You don't have to memorize it. I'm not going to ask you to repeat it. I just want you to know, like, this is based in reality. This is based in fact. So, if we have these two segments that are tangent to this pretty circle, that means these are right angles. That means I could draw a line from the circle to the outside Y, and I tell you that we have two congruent triangles now because they have radii of the same length. They are sharing a side here. And it doesn't look like it because I did a horrible job of drawing, but this is a right triangle, so these two triangles are congruent by hypotenuse leg, which means their corresponding parts of congruent triangles are congruent, meaning those two sides, XY and ZY, are congruent. Cool. Let's do an example with this theorem at 10.3. Alright, here is our example. We're going to find X, Y, and Z in the diagram. We've got a circle. We've got two lines that are tangent to that circle. I know that because there are right angles here. These are the radii. And this 4y minus 4 is relating to this segment here. And this 5y minus 1 is relating to this segment here. Okay. Fine. X and Y and Z. Well, X, that's pretty obvious, because X is the radius of the circle, which is the same as this radius, 10. So X equals 10. And our ice cream cone theorem, right, we're just looking at this guy and this guy. And our circle, this is my kind of ice cream scoop. We've got this little tiny cone and this big giant scoop of ice cream. Well, our ice cream cone theorem says that these segments that are tangent to this circle are equal to each other. So 5y minus 1 equals 4y minus 4. Quick solvey, mathy. Subtract that 4y and we'll get y over here. Add that 1 to both sides. Negative 3 Is that a weird answer? Yes. Is it real? Apparently. And last one. Hold on. There's just no way. You know why? Because I wrote the problem down wrong. This is supposed to be 4y plus 4. It's always good to go back and check when your work doesn't make sense. So this is supposed to be plus 4. So when I subtract 4y from both sides, I still get the 5y. And I add 1 to both sides. And then I get positive 5. Okay. That I'm here for. Totally here for. Now I'm going to find z. Using Pythagorean theorem, you're correct. What a bunch of geniuses. Just a quick little how and why is that working. We've got a side that's 10 units long. We're looking for z. We just figured out 5 is what y equals for real. So we plug that in. We get 5 times 5 is 25 minus 1 is 24. And then we Pythagorean theorem this action real quick. Hundo plus 576, was that right? Pretty sure. Add those together, we're going to get 676 is the squared. And then I'm going to take the square root of that. And we're going to get, oh, that's pleasant. Z's 26. What a nice, pretty whole number you are. We got our x was 10, because that was the same as the radius. Y finally was 5, and z is 26. Just realized my face was covering a bunch of that goodness. Alright, scholars. That's all the material for today. I hope you enjoyed this introduction to circles and their segments and whatnot. I love you, I miss you, and I will see you next time. Peace out.